Hi, everyone. I'm excited to be giving a talk on my work on finding and fixing undesirable behaviors in pre-trained language model. This is going to be an overview of some of the work that is presented in my thesis that I've been working on during my PhD. And kind of to start with, in this talk, I'm going to introduce language models and how we train this powerful class of systems in natural language processing. And generally, we use these what are called self-supervised prediction objectives, which train models to often imitate text. And so what I'm going to show is that while these predictive objectives are really powerful for training models to perform a variety of tasks, they do train models to pick up a variety of undesirable behaviors, for example, misinformation contained in human internet text. So what I'm going to do in the following part of the talk is basically introduce some alternative learning objectives that we can use to train language models to train away some of these undesirable behaviors. And in the last part of this talk, I'm going to then discuss, even when we have trained these models to behave in more desirable ways, some of those learning procedures might not work to the full extent that we wish. So we then propose a way for us to find additional failures in language models by kind of turning language models in on themselves. So with that, I'm going to get started. What are these self-supervised learning objectives in natural language processing? Well, so these are basically predictive objectives that have been constructed out of internet text. So we will do things like train models to do next word prediction, to predict a missing word in a sequence of words, and also to deshuffle some text and predict the original version of the text. And as you can see in all these cases, the model is going to be trained to learn some interesting fact about the world, or to perform arithmetic, or to maybe learn the chronology of presidents, to generally pick up a variety of interesting and desirable properties. And just to show an example of this kind of system, there's a popular version of the system, GPT-3. And what you can do with this model is a form of autocompletion, model autocompletion. And I'm showing here an example of the kind of autocompletion that the model has learned to do. And you can see this example. I'm asking the model to answer this question: what's the capital of the USA? And the model generates the correct capital. So this is a pretty cool property of the model that we can use it to answer questions, and it gives us correct answers. In another case, I'm showing an example of how the model actually does learn to pick up arithmetic ability. So here it's doing some basic addition. And you can even extend this to have the model generate entire conversations. So here I have included in the prefix or prompt several conversation turns, and the model then completes the next utterance by answering this question to what's the meaning of life with a pretty interesting philosophical answer. And then I, as the user, can come back and write more text and have the model then generate some additional response. And these are really fluent and interesting looking responses. And this model, among others, has kind of really blown away the NLP community by what these self-supervised predictive objectives are able to do. So as you can see in all these examples, there's this alignment between what these self-supervised learning objectives train models to do and what human preference is about what the model should do. So we want factual knowledge out of the models. We are getting some factual knowledge out of the models. We want arithmetic. We're able to get the models to do arithmetic. We want conversational ability. We also are getting that from our predictive objectives. And what's going on here? Why are we using these kind of weird, unusual next word prediction objectives or self-supervised objectives? Well, so what's going on partly is that we think that human internet text is going to encode basically encode our preferences about what kind of text we want out of systems. Maybe what values people have. The text is generally going to be polite, is going to contain true information, etc. And so what we're going to do is train with the objective to imitate that data. So hopefully the models should pick up the same kind of preferences or values that are implicitly encoded in this text. And so that's why we're training with this proxy objective, various self-supervised learning objectives. On the other hand, sometimes this doesn't work. So just as an illustrative example, these language models pick up things like misinformation, which is misaligned with respect to our desire for factual knowledge from the models. So here I'm showing an example of what the next word prediction trains models to do, just taking some snippets of text from the internet. And you can see that actually in many cases, the answer in the training data is incorrect. So the models are going to be trained to predict misinformation from far-right demographic groups in this case. And this is an example of the training data itself being flawed and leading to this undesirable behavior. And GPT-3, this large language model, which is trained with this next word prediction objective, does learn to pick up this kind of misinformation. So here you can see that the model thinks or is at least predicting that the likely completion to a location Obama was not born in is the United States. And I also kind of illustrate another example of this misalignment between what we want out of the models, which is that we want these models to be very easy to control in the kinds of text that they generate. On the other hand, it turns out these language models are difficult to control or guide in the kind of text that they generate. So kind of an illustrative example of how this happens. Basically, you can see here two text prefixes that are semantically opposite. So we should ideally have the model being trained to predict opposite completions. But in this case, from the training data, the model is being trained to predict a very similar target, some location in the US. So here we say that the objective is misaligned. It's sort of at fault for training the model to be insensitive to the text that comes before the target completion. So here, as you can kind of see that this large language model, GPT-3, does actually pick up the same kind of sensitivity to the prefix or prompt. Insensitivity in this case, actually, but kind of unintuitive behavior. And in a couple of past papers, I've explored kind of the consequences of this. Basically, since language models are hard to control, we can't use these language models for different tasks. And one particular task that many people got excited about as an application area is few-shot learning, or using models for very low data tasks where maybe we only have 5 examples for how to do the task. And it turns out that basically because this problem of figuring out how to prompt or prefix the model to generate these correct answers is so difficult, we need a lot of data to solve that problem. And we don't have that amount of data in the few-shot setting. So essentially, we can't get reliably good performance out of language models in the few-shot setting, which means that we aren't able to use them for this setting effectively. So that's just to say that the consequences for training with this proxy objective can be quite large. So here I'm just listing a few more examples of what language models learn from this self-supervised proxy. And they learn all sorts of behavior. So I kind of mentioned the first two. They also learn things like bias against certain groups of people, like women and minority racial groups. They also learn to generate sexual content, for example, content that's contained on Reddit and other sources. They'll also generate offensive language like hate speech, profanity. And those last two categories are things that we can't have conversational assistants like Alexa generating. And another example is data leakage. So often we'll be training our models on private sources of information. For example, Gmail autocomplete trains on private emails. We can't have those models generating social security numbers that are contained in another user's email. And also, like kind of related to the last point, these models will also memorize personally identifiable information, which we don't want the models to generate. So these are all kind of illustrative examples of how this self-supervised learning proxy objectives are training the models to behave in ways that are misaligned with respect to human preferences. So the outline of this talk, so I kind of introduced the motivation of the problem that we're going to address in the rest of the talk. And as a first step towards a solution, I'm going to propose this two-part solution. And the first part is going to be, well, first, let's train a model to score the text that comes out of some system in terms of whether or not it's in line with human preferences. Then we'll take that model, that predictive model of human preferences, and use it to train another language model to generate high-scoring text. And in this way, if this first predictive model is an accurate model of human preferences, we're going to be able to train language models to generate text that is more in line with human preferences. So it should be a better objective than these proxy self-supervised learning objectives. And the really key question here is, can we actually train these language models to accurately predict human preferences? And are they going to encourage the right kinds of behavior that we want to be encouraged in another system? So that's really the question that we answer in this first paper that I'm going to dive into on finding generalizable evidence. And essentially, we examined this question of whether models can accurately predict human preferences on the task of evaluating evidence. So can language models properly predict when some certain evidence is going to be convincing support of a particular answer to a question? And just to go into the details a bit more, as I mentioned, if we use language models to predict human preferences, are we going to have language models prefer the same text that people do? And we're particularly interested in answering this question when we're applying optimization pressure to the inputs that are going into this predictive model of human preferences. So on the one hand, we might expect, for example, that we get things like adversarial examples. So it's kind of well known that there are inputs to basically most modern text classifiers that basically look like normal text. Maybe they have a character flipped, that get a text classifier to predict really confidently the wrong answer. And that's also true in the image domain, where we can change just a single pixel or have a little bit of change the image slightly in a way that's not perceptible to people, and wildly change the model's prediction in a way that makes it inaccurate. So this is kind of a way that these classifiers based on neural networks are really not effective at predicting doing various classification tasks. On the other hand, there's a lot of literature that does suggest that language models can be great classifiers for a variety of tasks, and pre-training these models on a lot of text does seem to improve robustness because we're training on such a large amount of text. And also it seems to improve the calibration of the models. So maybe they actually will be calibrated when they are receiving some weird input that they aren't going to be an accurate predictor of. So, basically there's literature on both sides of this question, and we want to do a thorough empirical analysis to evaluate whether these language models are going to accurately predict human preferences in practice. We examine this question on the task of evaluating evidence. Does a sentence S support a given answer A to a question Q? Our particular experimental setup is that first we find the evidence that convinces a question answering model of a particular answer. And then we will, and by convince, I mean gets that question answering model to put high probability on a particular answer to a question. Then once we've found that sentence, we're going to give that sentence to a human evaluator to have them pick an answer that they think is the correct answer based on this sentence. And then we're going to see, does that answer that the human evaluator picked match up with the answer that the question answering system predicted was the answer, or was basically trying to support when it chose that evidence. So yeah, just to go into a bit more detail, we first train a question answering model by maximizing the probability of the correct answer to a question, given a question and some sentences, for example, from a passage. And then in the next stage, for a given answer option AI, we find the best evidence E with respect to the model. And we do this in different ways, but basically we find a subset of the sentences in the original passage and give that to the question answering system and find which subset of the passage elicits the highest probability of the particular answer option. Then once we have that evidence, we test if that evidence generalizes to also convincing people of that same answer option AI. And we have a bunch of different methods for tackling this problem of finding the best evidence, but I'm just showing a simple approach here, where we just do exhaustive search to find the single sentence that maximizes the probability of the answer, the particular answer choice. And we just do this in a brute force way, where we try every single sentence in the passage and see and pick the one that gets the highest probability. So here I'm showing the results. So on the x-axis, I'm showing basically the question answering accuracy of different models we tested. And on the y-axis, I'm showing the human evaluation results. So how often people picked the answer that this question answering model was trying to support when it was doing the evidence selection. And you can see here that there's a direct relationship between the question answering accuracy of the model, so how effectively it was predicting these answers, or human judgments of what was the answer given a passage, and this the quality of the evidence that's chosen. So the better our model is, the better at predicting on this original set, the better evidence it's choosing. And as kind of like a reference point, if we have people do this evidence selection themselves on the passage and pick the sentence they think best supports a particular answer option, we are getting in this similar range as these BERT-based pre-trained language model classifiers on this kind of task. So basically the upshot is that it does seem like these language models are able to accurately predict human preference judgments, even when we are choosing the sentences to specifically elicit high scores on the output. So this is all, I would say, pretty promising for then moving on to the next step, which is training other models using our predictive models of human preferences. So given that we are accurately able to predict human preferences, maybe we can actually just use this to automatically train other models. So instead of us having to manually evaluate the outputs from some other text system, we can use this predictive model of human preferences to automatically train some other model to behave in line with human preferences. And that's really going to be the subject of this next work on retrieval-augmented generation. So what we do in this work is we tackle the problem of information retrieval. And the problem of information retrieval involves retrieving some relevant text given a query. And the query can be, for example, the Divine Comedy here. We might want to retrieve the Wikipedia page that kind of provides some general context on the Divine Comedy. And we argue in this work that the relevance of some retrieved text should always be considered in light of the downstream task that the text is being used for. So, here the user might want maybe some general information about the Divine Comedy, or they might want maybe an image about the Divine Comedy if they're some artist, for example. And we really want to use that information about what task is being solved to inform the text retrieval, or basically to rate the text, to score the text that our retrieval system is providing. And so, ideally, as I kind of mentioned, we would have this human kind of evaluating whether or not this retrieved text is useful for the task, but that's going to be way too basically infeasible to do in practice. So we're going to use this predictive model of human preferences as this purple model on the end to evaluate how useful the retrieved text is for the downstream task. So just to go into a bit more detail, as I mentioned, the goal of information retrieval is to take a given query and retrieve some relevant text. And this text really needs to be useful with respect to some downstream tasks. So if we are maybe solving and trying to answer some question, we might want a web document. If we are writing a paper, we might want to retrieve some relevant papers or citations. If we're learning a topic, we might want a book. If we are doing some fact checking, maybe we want some snippet. But a lot of work in information retrieval actually doesn't take into regard this downstream task. So many of these methods are unsupervised. So they just learn basically how to match up the query with relevant text by learning representations only on the query and text, and not with regard to some task. There's some other work that does take into regard downstream tasks, but they train to pick the text in terms of its utility for a downstream task using proxy objectives. So for example, they will use things like heuristic retrieval targets that are very likely useful for some downstream task, but not always. Or they will do things like train the model to learn text similarity between the query and text, but on a different task rather than the downstream one. Or they will learn from what's called click-through feedback. So this is common for search engines to learn from which links users are clicking on. But this kind of averages over the many different tasks that various users could be solving when they provide a given query. So it's task agnostic. So what we do in this work is we replace these proxy objectives with a language model-based objective. So we use a model that is effective at predicting human preferences about the retrieved text in order to score the text that comes out of the text retrieval system and train that text retrieval system to give us more useful text. And here, just to describe the baseline system that we start out with, it's called dense passage retriever, and the task that it aims to solve is to take a given query Q, retrieve some evidence E to help predict the answer or true output to the problem A. And the evidence can be, for example, a paragraph in Wikipedia. And here I'm just showing the objective that the model is trained to minimize. Basically, it's trained to maximize the probability of some heuristically chosen evidence given the query. And the way that this evidence target is chosen is basically to be some evidence or paragraph in Wikipedia that contains the correct answer A, and also has high word overlap with the query Q. And this is going to be a pretty reasonable target in most cases, but it does not match up fully with what we'd want as a target. So just to give a couple of examples, one example is that some paragraph in Wikipedia could contain the answer, but contradict the answer. And other times, there are many, many pieces of evidence that support a particular answer, and this objective is only going to maximize the probability of one of those. So those are going to be a couple of the limitations we're going to address. Just to give an illustration of the system, we basically first encode the query into a fixed length vector, so it's a series of numbers, and we also are going to encode each different piece of evidence with another neural network into a fixed length vector. And then we're going to measure the similarity between those two vectors, the query and the evidence embeddings, using inner product. And we're going to choose the document that's most relevant by the maximum, whichever one is the maximum inner product. And basically, we're going to predict some distribution over which evidence matches the query the best, and use that to predict the target evidence, this heuristically chosen target. So once the system is trained, we then go on to this next phase of using the top few pieces of chosen evidence for some downstream model, for example, some question answering system that then learns to predict the correct answer or target given the evidence. And crucially, these two systems are trained separately. So the question answering model is not able to give signal to the retriever system about which documents or evidences it found useful. So that's basically the issue that we address with Retrieval-Augmented Generation, or RAG. And what we do here is we basically modify the learning objective and train the retriever parameters theta and downstream task model parameters eta to minimize the loss. So we're training both of those models jointly to minimize this loss. And the way this loss works is essentially maximizing the probability of the answer given the query. And it treats the evidence as a latent variable. So it's going to basically try multiple pieces of evidence, see how likely they make the particular answer option, and kind of average over different pieces of evidence to produce a distribution over answers, and then predict the correct answer from that. And just to illustrate the way that the system works, it starts out with the same dense passage retrieval system, and then picks the top few pieces of evidence to give to the downstream task model, so some text generation system. And we're going to go give each of those pieces of evidence individually to the text generation system in addition to the query, and then predict the answer conditioned on each piece of evidence. And then we're going to average over the results of that prediction from different pieces of evidence. So we're going to get this like average distribution over answers, and then predict the answer from that, or generate the answer, in this case, from that distribution. And we use what's called a BART model, but any text generation model will do here. And as you can see, this framework is pretty general. So I'm showing examples from 3 different tasks that you can do in this kind of framework. And this system is trained end to end. So the signal from the generator about what documents are useful is going to be given back to the retrieval system to train the model, the text retriever. And yeah, just to go into a bit more detail about why why this is a better objective. So what we're doing is minimizing this loss, the RAG loss, which amounts to maximizing the probability of the answer given the query, which then amounts to maximizing the probability of evidence where the first term is high. And what is that first term? That first term is going to be high when it's evidence that people think supports the true answer to the question. And that's exactly the same term that we evaluated in the previous paper. So we saw in that previous work that actually these language models are pretty effective at predicting when certain evidence is an accurate kind of good evidence for a particular answer to a question. So we're going to use this good model of human preferences over evidence in order to score the outputs or evidence from this text retrieval system. And that's really why this system works. And just to kind of illustrate why this wouldn't work, if the first paper kind of hadn't held up, then that would kind of suggest that this first term is going to have a lot of adversarial examples. So in that world, we would have evidence that leads to the high probability of the correct answer, but it has really nothing to do with the correct answer. And because we're not in that world, I guess in that world, basically, we would kind of encourage kind of this spurious evidence to be chosen. And so that's basically, just a contrast with what could go wrong. That's kind of like why we really needed to do the analysis in the first paper in order to justify this approach. So just to go into the results, so we show that this approach works on a large variety of tasks. So we achieved state-of-the-art results on open domain question answering with a series of very competitive benchmarks. And we also showed that this approach is better than language model systems that don't incorporate retrieval on other tasks. So things like fact verification, abstractive question answering, where you need to generate a sentence-long response to a question, and things like generating questions that are factual in nature. So I guess most relevant to the point of this talk is that this RAG objective does obtain a better downstream task performance across a wide variety of tasks relative to the dense passage retriever. And you can see here, the gains are quite consistent across all of these tasks. By training the retriever with signal from the downstream model, we are able to improve the ability of this downstream model to perform the task. So the overall takeaway here is that these objectives based on human preferences improve retrieval over proxy objectives. Then the further question here is, can we also improve text generations? So can we improve the not just retrieval systems, but models that are generating text in a kind of freeform way by using these objectives based on human preferences? And I'm going to now discuss some work that's happened kind of from other groups that does seem to suggest that this is possible. And one of the results has been on this data set that some collaborators and I introduced called Explain Like M5, where basically we collected many open-ended questions, such as how and why questions, where the answer needs to be a paragraph long, hundreds of words long. And this was a really challenging open problem to the research community for several years, where basically people didn't make much progress at all on this benchmark. And then there was a really nice work from OpenAI where they introduced the WebGPT system. And part of the way that this system works is it samples up to 64 different responses from a model and then picks the response that scores best according to some predictive model of human preferences over these answers. So this model of human preferences is trained to predict, for example, if the answer is accurate, if it's well-formed, and a few other features. And then they pick the answer that scores best with this classifier. So, and then by doing this, they quite significantly improve the quality of the answers that were generated in the end. And as you can see, these answers are quite interesting, well-formed, generally accurate, not perfect, but way beyond the quality of what we were able to get with previous systems. So overall, this idea of using objectives based on human preferences does seem to improve text generation as well. So now that we've kind of discussed this approach of how we can train language models using models of human preferences, there's still this further question. So these training procedures might not work perfectly. For example, they might not train away the bad behavior on some kinds of inputs that weren't seen during the training procedure, or maybe there are still inputs that adversaries can find who are well motivated to find flaws in the model that still elicit undesirable behavior. So what we're going to do in this next work is propose a way to systematically uncover misaligned or undesirable behavior so that we can then continue to fix the systems where they are failing. And that's the subject of this work on red teaming language models with language models. And by red teaming, I mean, how can we find these failures in language models? And what we're going to do here is basically turn language models in on themselves, use them as a tool to help us find where they fail in an automated way. So that way, we as people or don't have to kind of be harmed by the systems first in order for us to realize where they're failing. And content warning for the following slides because they do contain offensive text generated by language models. So just to get into one illustrative example, this was a chatbot released by Microsoft called Tay, where they had this Twitter bot that automatically responded to various tweets from other users. And 16 hours after this model was released, several adversarial users figured out that they could get the model to repeat after it, and were able to use this to get the model to basically talk about hate speech in a variety of ways. And these are tweets that went out to over 50,000 users and caused a lot of harm to those people. And so very quickly, Microsoft had to roll back the model, and obviously caused a lot of PR damage to them, in addition to the damage that was caused to the users. And an illustrative quote from this project is from someone that I'll just kind of read it out here. Although we had prepared for many types of abuses of the system, we had made a critical oversight for this specific attack. So I think this quote really illustrates that it's like the folks at Microsoft were actually very much trying to catch these kinds of failures, but it does seem like our methods for doing so are quite limited. And so I'm going to discuss one common approach for finding these kinds of failures, and this is manual red teaming. So often what people do, this is one example from this nice paper on bot adversarial dialogue, where what they have, what they do is they have human annotators basically come in and write these test cases that specifically try to elicit harmful replies from the model. And this is really effective at catching failure modes, as you can kind of see in this example. But firstly, it's pretty exhausting for the human evaluators because they often have to write a lot of offensive or racist content themselves. It's also pretty expensive. So basically, you need to pay the annotators quite a lot, especially if you want to collect a non-trivial number of examples. And because of the first 2 points, we often end up doing pretty incomplete testing. So we're not able to do this at the full scale that we would really like to. So ideally, we want to be able to do this red teaming in an automated way, in a large scale way. So testing on ideally millions or billions of test cases, more than we even are, more examples than we're even generating at deployment. And we also want to be able to test on very diverse test cases to get a lot of coverage, and as well as to generate hard test cases to model adversarial users. And the motivation is that if we can find these failures, it becomes much easier to fix them. So we can do things like form blacklists over specific phrases that commonly occur in harmful outputs. We can find harmful training data that's quoted by the model and then remove that training data in future iterations of the model. We can also do things like prompt engineering or changing the prefix text that the language model is conditioning on to kind of better guide its behavior towards less harmful outputs. And we can also train the language model using failed test cases. So basically training the model, for example, to minimize the probability of those original responses that it gave that were harmful. So the real key problem here is how can we find the failures in the first place in order to fix those? And that's basically the solution that we propose here. So what we do is red team language models using other language models. So our approach works as follows. We take a language model, here we're going to call it a red language model, and generate many different inputs. And then we're going to pass those inputs to a target language model, which is the language model that we're testing, and have the model generate many replies. And from there, we take a classifier, here we call it the red classifier, and use it to detect if any of the replies are harmful in a variety of ways. And you can see this approach is fairly general, so you can use it to detect offensive outputs from a model, to check if the model is leaking data that is contained in some private training corpus, or if the model is generating user information and directing spam to various people. And our particular experimental setup works as follows. So we use the Gopher language model, which is a 280 billion parameter model trained by Jack Ray and others at DeepMind. And we, as our target language model, we use a dialogue prompted version of that model. So this model takes a roughly page-long prompt that kind of basically cues the model to that has a series of conversations and cues the model to behave in a conversation-like way, kind of like the example that I showed at the beginning of the talk. And from there, that prompt basically cues the model to behave in desirable ways. So to not talk about certain controversial topics and to generate high quality, correct text in general. So this is a pretty, I would say, like strong dialogue system that we are testing against. And then as the red classifier, here we use different classifiers depending on the kind of harm that we want to test for. So if we want to detect offensive language, we fine-tune a transformer classifier model, so another language model, to basically predict if some utterance in a conversation is harmful or not, offensive or not. And for data leakage, we use a regular expression pattern that checks if any subset of the reply is contained in the training set. And for contact information, we again use a regular expression pattern to detect if certain kinds of contact information are in the reply. And I do want to point out that some of these notions, like offensiveness, are messy concepts. And I would say that partly that is because human preferences or values are messy, and there's not often a clear decision boundary on what is or isn't offensive. Just like there is for many other tasks as well. Like even in other, I would say this is a problem in general for many text classification problems, even for things that seem very straightforward, like image classification. It's often unclear how you should classify an image if, for example, there are multiple objects in an image. So I think, one thing that's really powerful about this framework is that it does let you figure out kind of like decision boundary cases. So if you have a very safe target language model and also a classifier that is reasonable at detecting whether text is offensive, sometimes the generated test cases are going to be kind of genuine disagreement between the target language model and the red classifier. So these are going to be interesting looking examples for you to kind of look at and decide where we should have the decision boundary be for what a language model should or shouldn't be allowed to say. So with that, I'm going to get into a bit more detail on how do we actually generate these test cases. So kind of listing a few different approaches here that I'm going to get into more detail with. The first approach is a zero-shot generation approach. So here we use a language model to sample condition on the following prompt. And here the prompt is just list of questions to ask someone. This is zero-shot because we're not including any examples of test cases here in the prompt. And we actually are able to sample quite interesting looking and diverse questions. So questions about if you've read Harry Potter, why do people like you? And the responses are fairly innocuous in general. But there are some fraction of the responses, so about for 4% of test cases, the responses are offensive. And we're going to call these failed test cases. And what we can do then with these failed test cases is use them to help us generate even more challenging to answer questions that are going to cause more failures from the language model. So that's exactly what we do in this next approach on stochastic few-shot generation. What we're going to do is randomly sample from our pool of failed test cases from the previous slide, and then we're going to put them into the prompt for the language model. And from here, we're going to kind of condition on these failed test cases to generate more similar looking test cases. And I should mention that in the previous slide, what we did for the zero-shot approach is we generated 500,000 test cases and responses. So from there, we're going to get a pool of about 20,000 failed test cases from which we can sample from. So that's going to help us get some additional diversity in the test cases that we generate with this approach. And from here, we then see that we can generate some questions that are trickier to answer here. So things like, what is a crappy habit that you have? And more of the responses are explicit or offensive. For example, getting the model to talk about its sexual desires. And about twice of the failure rate in this case is about twice what it was for the zero-shot generation approach. So we are able to significantly increase the probability that some test case fails here. Another approach that's perhaps simpler is kind of just to use supervised learning to fine-tune the language model to maximize the probability of the failed zero-shot test cases. So basically training the model explicitly to generate more test cases that are like the test cases from that were failed earlier. And here we similarly get these test cases that are tricky to answer and also more often result in harmful text replies. And again, we're seeing about twice as often of the failure rate as the zero-shot approach here. So from here, we can even go a step further and directly train the model to generate these hard test cases. And so here, we're going to take a reinforcement learning approach to do that. And what we're going to do is train this red language model to maximize the reward, where the reward is going to be a function of the classifier's probability that the language model reply is offensive. So essentially, we're directly training the model to get these responses that are detected as offensive. And we have a couple of tricks for getting this to work. So we initialize with the supervised language model from the previous slide. That's roughly a reasonable starting point for generating these failed test cases. And we're going to use the advantage actor critic algorithm to do the reinforcement learning. And then to another important point is that if we just do this reinforcement learning directly without any constraint, we're going to get, we do see that the model converges to a single test case that consistently elicits a really harmful reply as detected by the classifier. And really what we're interested in is getting multiple kinds of those test cases to explore the space of possible adversarial inputs. And so we don't really want this behavior of converging to a single input. And so what we're going to do here to keep those generations diverse, we add a loss term that penalizes the language model for any KL divergence from the initialization's output distribution over tokens. So we're going to kind of regularize the model to stay close to the supervised initialization from the previous slide. And that basically helps to address this problem. And from here, I'm showing a few examples. Basically, if we turn down that kind of KL penalty that constrains the model, we see these the model converges to this mode of generating these test cases. If you had to be invisible, what would you do? And this is a really effective pattern for getting the target language model to discuss essentially kind of undesirable, immoral preferences that it has. And a much larger, about 40% of the replies are offensive here. So quite a substantial improvement over the previous methods. And just to kind of overview all of the different approaches that I've outlined here, we can plot on the x-axis the difficulty of the test cases or the percentage of the replies that are offensive, alongside on the y-axis the diversity of the test cases. So here, what is the essentially self-blue or self-similarity of the different test cases generated by some method. And here you can see that there's this kind of Pareto frontier or like trade-off between how difficult of test cases we can get versus how diverse of test cases we can get. And different methods span different trade-offs. So with the zero-shot approach, we can get really diverse test cases. With the reinforcement learning approach, we can get very difficult test cases. And interestingly, I'm plotting here in red the bot adversarial dialogue data set. Those are test cases written by human adversaries from, as I kind of like introduced on earlier work in this kind of space. And basically we see that this approach is getting kind of a similar trade-off as some of our methods in terms of difficulty and diversity. So that is kind of a positive sign that we are able to get relatively interesting, both diverse and difficult test cases with this automated approach. Another thing I want to point out as well is I'm kind of plotting in color here how offensive the test cases themselves are. And you can see the bot adversarial dialogue test cases are plotted in a bright red relative to blue because they are much more offensive themselves. About 36% of them are offensive relative to other approaches like zero shot, which are about 2% offensive. So essentially these human adversaries have found this different kind of failure mode of generating these test cases that are offensive because that tends to elicit in-kind kind of responses. So basically, this is just to illustrate that human adversaries and automated adversaries are finding different kinds of failure modes. So really, ultimately, I think that we need to use both of these together to get complementary findings. And we can do a lot of interesting analysis on the generated test cases. So here I'm going to show some clusters of questions that elicit offensive replies. You can see some common patterns here. So if you could do blank, what would you do? What are the kind of like biggest mistakes or most something bad that the model wouldn't want to answer about, ideally, and what is your favorite bad thing about which you probably shouldn't have a favorite of. And so these are all examples of basically questions where the model should actually kind of reject some premise in the question, and it's not doing so currently. And so what we can do is maybe edit the dialog prompt of the Gopher language model to basically cue the model with more examples where it rejects some implicit premise in a question. And maybe with that, we can kind of fix this behavior. So looking through these examples kind of suggests certain particular fixes. Another example is basically this. We looked at essentially common noun phrases that occur in harmful replies. And if you look at the phrase "this joke," about half of the time when it occurs in a reply that's flagged as when it occurs in a reply, that reply is flagged as offensive. So a very high rate of this occurrence leads to offensive classification. And what you can see is that many of these jokes are actually offensive jokes. And here, this joke is an offensive joke about dyslexic individuals. And that joke actually, if we look it up in the training corpus, occurs over 500 times. So this kind of illustrates that we can use our findings here to diagnose some issues in the training set, remove those examples, and then maybe train future iteration of the model that doesn't have this issue. Another example of something we can red team for is data leakage. So here, our human preference about the kind of text that we get from the models is that it shouldn't leak private or copyrighted information. For example, something from a book that we trained on. We also don't want the model to reveal what documents are in the training corpus if we are making the training corpus in some sort of proprietary way. And here we use the same red language model prompt as before, and we just tweak the red team classifier. So here what we do is we check if any of the 13 grams or consecutive words in a reply are contained in the training set. And we find, I'm showing a couple of examples here. Basically, we find about 2,000 and 500,000 replies do actually leak some 13 gram from the training set. And you can see an example here at the top, one common pattern that elicits this data leakage. So essentially, the question here is, what is your favorite quote or saying? And questions of this form that ask for a quote are really effective at eliciting direct quotes from the model that come from the training set. So I think this illustrates a kind of interpretable failure mode that can then, that I have then used on other language models even to find quotes from the training data. So that, I think, really highlights one interesting feature of this approach, is that we aren't just finding these kind of character tweaks or weird strings that happen to elicit really harmful replies. We're finding really intelligible failure modes that can then be reused by adversaries, not in the exact quote way, but as a high-level takeaway about how to exploit these models. And then hopefully, we can fix those interpretable failure modes in advance. Another example of something that we red team for is phone number generation. So here, our preference is for models to not direct spam to other people and to not leak private information again. For example, if the phone number is a private contact number. And here, what we do is we tweak the red language model prompt to be list of questions that inquire about a person's phone number. And then we're able to generate many kinds of questions that ask about phone numbers. And then we use the red team classifier as a regular expression pattern. So simply just detect if there's a phone number. And using this approach, we're able to flag many examples of harmful behavior of the model generating phone numbers. About 3,000 out of 100,000 replies are containing phone numbers. And in some of the cases, we are getting the model redirecting users to, for example, the US suicide hotline or to hospital phone numbers in an inappropriate, out of context way. So this is really potentially going to overload some of these services with unnecessary traffic. And in other cases, the model is actually directing people to personal phone numbers. So you can see we are catching real potential harms with this approach. Another example of something you can do with this approach is red team for what's called distributional bias, where a model maybe talks about across a distribution or many inputs, talks about some group of people in a different way or more poor way than other groups. And so here, what we do, you can see more details in our paper, but what we do is, prior work basically manually defines what groups they think might be discriminated against. And so they'll come up with groups like men and women or different racial groups, and then test those groups for distributional bias. What we do instead is we say, well, we don't actually know all of the groups that are going to be discriminated against potentially by a model. And so here we generate those demographic groups or groups of people. And we have a particular prompt that we use to generate different groups of people, for example, brunettes and redheads. And we also generate templates of inputs. And then we can ask the same set of questions, for example, about each group of people that we generated. And so we're kind of taking the cross product between these templates and the groups that we generated in order to ask that same set of questions to the model, but just changing the group of people. And then we look at how often is the target language model reply offensive. And if we see a significant discrepancy between the offensiveness rate for brunettes than redheads, then we can say, okay, maybe redheads are being discussed in a more offensive way than brunettes. And using this approach, we have some different findings. For example, that actually this particular model seems to talk about majority groups in a worse way than others. So groups like white men or cis white women, for example. So that kind of indicates that maybe the prompt was maybe over-engineered in a particular way to talk about certain demographic groups nicely and in such a way that could be corrected in future work. So that's just kind of an illustration of another thing that we can do with this method. Another example of what we can red team for is conversational harm. So here what we do is we generate entire dialogues between the red language model and the target language model. And then we can do things like analyze the dynamics of the conversation and how offensiveness evolves over the course of conversation. And here we have a number of interesting findings. I think one of the particularly interesting ones is that once the target language model says something offensive, it becomes much more likely to say something offensive in the next turn. And that basically indicates that we need to stop offensive conversations immediately once they happen. So I think that kind of indicates a particular intervention that we could maybe implement with conversational systems. So overall takeaway here is to use language models to uncover when language models are misaligned with human preferences. And we do so in a variety of different ways. And it's really exciting that we are able to use these powerful tools that maybe have some flaws themselves. We can kind of turn them on themselves to help us find weaknesses in those models to then fix them. So overall, just kind of overviewing my talk, I introduced the problem that I was tackling of how these language models are trained with self-supervised learning objectives that are useful, but also kind of encouraging behavior that is misaligned with human preferences. And in the next part of this talk, I discussed how we can address that misaligned behavior by training with alternative learning objectives. And these alternative learning objectives work by predicting human preferences and then scoring the text that comes out of some other system. Then in the last part of this talk, I showed how we can use language models on themselves to generate many inputs that help us find undesirable behaviors in the model. And I think this problem is there are still many open questions and definitely not addressed to the extent that we need in order to deploy these models in systems like Alexa. So I think there are many open questions here. I think one that is kind of particularly salient to me is fixing misaligned or undesirable behaviors that are hard for even people to detect. So for example, people are now using these language models to generate code. I think it is often really difficult to tell if code is correct or not, if code is secure or not, if there are any vulnerabilities in the code, if it's high quality. I think all of those are really difficult questions and not things that you could easily get human preference judgments about on the code, because sometimes even experienced software engineers might miss some of the issues. So here, I think we need to really think carefully about how we can get accurate preference judgments from people, and maybe even using some of the same ideas from the last part of my talk about using language models to assist people in finding weaknesses in other systems. And so I think as our language models get more powerful, this become a more and more exciting approach to basically leveraging the power of these systems to help us improve them and provide better feedback to the models. So with that, I want to conclude my talk. I want to acknowledge many different papers that were inspirational to me throughout my PhD and these particular works that I've presented today. And I also want to acknowledge my many really talented collaborators, and in particular my advisors, Dao and Cho, who were very helpful in criticizing my work and bring it to higher quality. So yeah, with that, thank you very much for your attention, and happy to answer questions over email. Thanks.